Displacement current was the last piece to complete Maxwell's equations, and it was a concept that Maxwell conceived. James Clerk Maxwell was born in 1831 in Edinburgh. In the mid-1700s, the Clarks acquired an estate by the name Middleby by marriage, on the condition that whoever inherited the estate would add Maxwell to his name. James Clerk Maxwell inherited that estate, so Clerk Maxwell is really his last name. Here's an early image of Maxwell, probably about the time he wrote Faraday and sent Faraday a copy of a paper he wrote entitled On Faraday's Lines of Forces. I'll talk about that paper a little bit more later. Maxwell looked quite different when he was older, and his look was the inspiration for the look of the rock band ZZ Top. In this photo, Maxwell is holding a color wheel. At this point in his career, he was doing research on color vision. In the video Color Vision, I talk a little bit about Maxwell's work on color vision, and it will also talk about additive and subtractive color mixing. We have been referring to Maxwell's equations, but so far in the development of those equations, we have not encountered Maxwell. We will now talk about the final piece to Maxwell's equations, the piece that Maxwell added. Ampere's circuital law tells us that the integral of h dot dl around a closed path is equal to the current that's flowing through the surface whose perimeter is defined by that closed path. It was known that something was missing from that equation. Let's assume we have a DC current flowing in a wire, but let's attach that wire to a capacitor. And now if we choose as our surface a surface that goes through the capacitor, we see there's no actual current flowing through this surface now. Maxwell determined what term has to be added to the right-hand side of Ampere's circuital law to account for such situations. With a DC current flowing, the charge on the capacitor is going to be increasing. That increase in charge, that dq dt, is going to equal the current that's flowing. If the current flowing is 1 amp, you're adding 1 coulomb per second to the plate, so dq dt will be 1 coulomb per second. The electric flux density field is just the charge density on the plate, so it's the total charge on the plate divided by the surface area of the plate. For the charge on the plate, let me substitute the electric flux density field times the plate area. For simplicity, I won't continue to include the time dependence of the charge and the electric flux density field. Since the plate area is a constant, I can move it to the left of the differentiation, so the current flowing is equal to the plate area times the change in the electric flux density field with respect to time. An area times a current density gives us a current. So Maxwell called this partial d with respect to time the displacement current density. Maxwell set the integral of h dot dl equal to the sum of the free currents plus the displacement currents flowing through the surface. Ampere's circuital law states that the integral of h dot dl around a closed surface is equal to the integral of the free current density dot ds plus the displacement current dot ds over the surface whose perimeter is the path of integration of h dot dl. Going back to this figure, when our surface cuts through the wire, there is not a second term here because for DC current flowing, the electric field is constant, so the partial of D with respect to time is 0. So the only contribution comes from the integral of J dot ds through the wire, which is the current flowing in the wire. For the surface that cuts through the center of the capacitor, there's no free current flowing, so this first term will be 0, and the contribution will all come from the summation of the displacement current density through the capacitor. If we take Ampere's circuit law in integral form and on the left-hand side rewrite it using Stokes' theorem, we can see the point form of Ampere's circuit law is the curl of H is equal to the free current density plus the displacement current density. So here we finally have the complete set of Maxwell's equations. Maxwell never saw this set of 4 equations. Maxwell had 20 equations that contained 18 unknowns that he worked with. Those equations are shown on the left here. His equations included the electrical potential and the magnetic vector potential, which we didn't even introduce this semester. If we look at Ampere's circuit law in point form, we see he wrote it as 3 equations because they didn't have modern vector notation. So gamma would be h sub x, alpha would be h sub y, and beta would be h sub z. He would use p for j sub x, q for j sub y, and it looks like an r here for j sub z. Maxwell died in 1879. In 1883, Oliver Heaviside introduced the modern vector notation that we use today. In 1884, Heaviside consolidated the 20 equations that Maxwell was using into 4 equations and eliminated the electrical potential and the magnetic vector potential from those equations. In 1864, Maxwell used his 20 equations to predict electromagnetic waves. It wasn't until 1887 that Heinrich Hertz experimentally verified the existence of these electromagnetic waves. Oliver Heaviside was only employed briefly during his life as a telegraph operator. He spent most of his life living off his family and doing electrical engineering. He had a habit of alienating people and so was not very well liked, which could explain why he is not better known today. It was less likely for others to give him credit or assign his name to the things he demonstrated. I will put up PDFs of 2 articles. One is about the life of Oliver Heaviside, and the other one is about the long road to Maxwell's equations, in case you're interested in more of the history. Earlier in the semester, I talked about Michael Faraday and how he didn't have a formal education beyond simple math, reading, and writing. Other scientists highly respected Faraday's experimental abilities, which led to many discoveries. But they ignored Faraday's theories and explanations because he didn't have that pedigree from attending a college like Cambridge or the University of Edinburgh. One of the concepts Faraday came up with, which was ignored, was the concept of fields. Clerk Maxwell was in the next generation of scientists and didn't ignore Faraday's ideas. In 1857, Clerk Maxwell, who was in Scotland at the time, sent Faraday a copy of a paper he had written entitled On Faraday's Lines of Force. These lines of force are what today we refer to as electric and magnetic fields. Faraday was 66 years old at that time and thrilled, although he probably had difficulty reading the highly mathematical paper. In response, Faraday sent Clerk Maxwell a copy of a paper he wrote on proposed gravitational lines of force, an idea other scientists thought outrageous. In 1860, Clerk Maxwell took a position at King's College in London. He therefore was able to meet Faraday and attended events at the Royal Institution where Faraday was director. We are now going to look how Maxwell's equations lead to the existence of electromagnetic waves. But first, I'm going to put up a video that reviews the concepts of waves.